Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to chair the next session. That's going to include talks by Michael Cohen, Matt Utendale, Johannes Kopf on big pictures, and Daniel Shinsky on image guide optimization. First up is going to be Michael Cohen to kick off their talk.
Great.
You should send me. Are you publishing these?
Okay, so we're going to do a quick tag team, and hopefully the microphones, and there's some other technology that seems to have just crashed, but hopefully it'll all work. I'm going to take a half an hour and talk to you about something that a bunch of us are very passionate about. This mostly grew out of a project last summer and has continued on. And the idea is to create very, very, very big pictures. For example, this picture here is one where Matt and I climbed up to a building on Capitol Hill in Seattle and took this panorama. In fact, taking this panorama involved taking about 800 individual images, which were all assembled into a very large image, in this case about 3.5 billion pixels. Now, of course, what you're looking at is not 3.5 billion pixels, and we're going to spend a lot of time talking about how to deal with that. Like, what do you do with 3.5 billion pixels? Another aspect of these images, well, one thing you can see here is this little square, this black stripe, is there because at some point the battery in the camera shut off without our knowing it, and the camera was on a mount that was kind of scanning this scene. So this gives you an idea of what 8 megapixels looks like, about the size of it in that image. If we zoom in on this image, of course, there's a lot more pixels than you could see. In fact, we can see the guy driving this crane. This crane, if you had a sharp eye, you'll notice is broken in places, and that's because of this time difference as we were scanning the scene. Would have been nice to have got his cell phone number off his cell phone to call him up to have him stop, but couldn't quite resolve that at the time. The other thing is this is a very wide-angle image, and displaying a wide-angle image is problematic as well. If we were to simply map this image to a flat screen in the normal way by doing a perspective projection, it would look very distorted. We'll talk about that issue as well and how we deal with that. And finally, there's a huge variation in radiance across this scene. When we captured this scene, we simply let the camera do auto exposure, and in fact there was about 1,000th of a second shot when it was pointing at the sky versus these dark regions where it might have been down to about 1/20th of a second. So there's a very wide range of dynamic range in this image, and we want to be able to deal with that as well, both when you're looking at the full panorama and when you're looking at individual parts of the scene. And so these images, to me at least, one reason I'm so excited about them is the fact that I've spent, not just because of doing research, I've probably spent 2, 3, 4 hours looking at this image. And I've seen other people sit down in front of this image and look at this image for a long time. In a way, this image is, in terms of its a piece of media, it's almost like a movie, something you might watch for 2 hours and go and try to explore things. And I think there's a lot of opportunities to do some very artistic things with this. And that's part of the things we'd like to do in the future. So since it's not really a single image, is it an image of a guy driving a crane, or is it an image of a skyline? Is it an image of an airplane sort of off in the sky? What is this an image of? It's really all of those things, and yet it's a single image in some other sense. And so this really leads to the need for a viewer. You really have to have a viewer to explore this image. It's not just an image I can just kind of hold up on a piece of paper in front of me. And we'll spend a lot of time talking about the viewer, as well as issues on how we capture this. So I'm going to step down and let Matt talk about how we actually capture these.
Okay, thanks. So this is the capture rig that we ended up with. What we wanted to do, in order to scan these scenes, we wanted to capture as many pixels at a time for each photograph, and we also needed a very long telephoto lens. So we bought a Canon 1DS Mark II, which is 16 megapixels. We put a 400 millimeter lens on that. And the first couple attempts at capturing a scene, we realized we had this sort of massive piece of glass that we were trying to rotate, and it wasn't stable. It would vibrate after every tripod move. And we thought about it a little bit and noticed and thought that, well, there's another community out there that does something pretty similar. It's the amateur astronomy guys. And we actually got Meade to donate us one of their rigs. And we took out the telescope and built our own harness in there and mounted our camera in there. And it turned out to be a great platform. There's a big community out there hacking on this platform. There's a lot of code for it, so we could program this exactly the way we wanted to. So it's the fun thing about working in computational photography is we get to go out and take photographs sometimes. And these are a couple of places we captured. This was the Cary Park scene in Seattle. For some reason, the cheerleaders were getting their yearbook picture taken there that year, so we had some a cheering unit. And this is a spot in Squamish, British Columbia, where Matt Brown and I actually hiked in, scrambled up some rocks for about half a mile with this 50-pound rig. And that's how we captured the chief image that we'll show a little later. Okay, so once we've captured the images with that rig, next we need to assemble them into a gigapixel image, right? And this is the pipeline that we use in order to do that. And I'm going to step into each one of these steps in a little more detail. Okay, the first thing, since we were controlling the capture process, we captured everything in RAW, and that was just huge for us. You know, like JPEG is sort of the bane of my existence in trying to write a stitching program that actually assembles JPEG images, because the cameras all do something different in processing their RAW images and generating JPEG images. So the beauty in going to RAW is that you can get right back to essentially a scaled radiance image. So we captured everything in RAW, and our entire stitching pipeline just worked from RAW through radiance. So this is sort of the color space of the camera, and the images straight off the camera in RAW. Right. The first thing we did after that is to devignette. Again, since we were controlling the capture process, we were able to pre-characterize the lens. And the way we did that is we have this integrating sphere upstairs, which generates a very, very uniform light field. We took a picture of that and just divide that out. Right? So it's pretty simple. Then we white balance. And the way that this works is I picked one point in the scene. I think it was... where was it? Down here someplace. There's Ichiro's shirt, and I said that's white, and I propagated that white point to all 400 images in this particular scene, right? So, so no difference in it. Like if we were capturing JPEGs, the camera would have picked its own white point for every single one of these JPEG images, and that's just we didn't have to deal with that problem here, right? Then we finally exposure balance. So we set up the camera in what's called aperture priority, so we fixed the aperture, but it was varying shutter speed as it panned this scene, right? So that it could expose appropriately for the different parts of this scene. There's a pretty wide range of radiance values in this scene. So at this step, since we were capturing RAW, stayed linear, and had a common white point for the entire scene. All we need to do is divide out that shutter speed in order to go back to a radiance map. Next, the rig was fairly precise, but it wasn't precise enough to give us exactly overlapping pixels. So there is an alignment step in this. We use our MOPS feature points here to extract features. We didn't have to search very far for the features because we had a pretty good idea where the rig was putting the images. And then we match feature points. And in some spots, like here, where we didn't have any features, we just trusted the camera, the rig's reported orientation. Right? Then we align. We end up with an aligned image in radiance space. So there's a high dynamic range image at this point. And we have to apply a tone mapping now to take it down to something that's displayable. And this is all 240 images of this particular sequence. aligned, that went through that process, and this is the tone mapped output. Right. Okay, so just to look at the this radiometric alignment in another way, here's the images from the rig. This is 800 pictures, just put down with the exposure values that the camera used, right? And that's what that mosaic would look like. And after our radiometric alignment step, we get, this is with no blending at all between the images, right? The way other stitching, the way other papers have done this in the past is to, apply some sort of Poisson blend or Laplacian pyramid blend or something. But we didn't need to do any of that because we stayed in the linear domain. And this is purely by careful radiometric calibration of the capture process. Right? So yeah, I should just mention the one other thing that we do at this step is also we run a graph cut seam selection to, if you later get to zoom into this picture, you'll notice that there's cars on the highway that are moving, and we can cut around those. The big, large features like the crane, the graph cut didn't help us because they span multiple images and they're moving. Okay, so the tone mapping process, we wanted to apply the tone mapper that we had in a paper last year at SIGGRAPH, but the problem is we're dealing with 3.6 gigapixels, 3.8 gigapixels. We couldn't apply that tone mapper as it was written on that large a data set. So, so the solution we came up with was to apply the tone mapper to a much smaller representation of the image, and got another paper at SIGGRAPH that we won't dive into too much today called Joint Bilateral Upsample, where we use the full resolution pixels to guide the upsampling process of the tone mapping parameters to generate a edge-aware exposure map, right, for the full resolution image. And that's our tone map result at 3.8 gigapixels. Okay, so that, I think I've talked about everything in this pipeline. We go to radiance, we finally output. And the last thing we do is we output a tiled representation of this image, right, so that we can stream it to our viewer. So our tiled pyramid looks like this. We output 256 by 256 tiles at various resolutions of that image. So at the coarsest resolution, you'll see 2 tiles. And at the finest resolution, down at the bottom of the pyramid here, we'll get the native sort of pixels out of the pipeline. And that is fed to the viewer, which Johannes will talk about next.
Okay, so having captured this enormous amount of data, the next question is how to view it interactively. And in fact, if you want to display these images on a conventional display, like a monitor or projector, there's a number of reasons why this kind of calls for a specialized viewer. And so first of all, these images have much more resolution than these displays can provide. And so a natural choice for the interface for the user is one where he can zoom into the image, dive into it, and pan around. So these are essentially the controls that we map to our mouse. And also, the dynamic range of these images is quite larger than a conventional display can show. So tone mapping helps here a little, but actually with an interactive viewer, we can provide a much better experience, as we will show in a minute. And another thing is that if you sit in front of your monitor, it fills about maybe 15 degrees of your field of view. And now if you want to display an image that has much wider angles, you have essentially to compress these angles to a smaller degree, field of view of your vision. And so this compression of angles is not possible without introducing distortions to the image. And we'll talk about that in a minute also. So another thing is that Michael said something, a couple words about this, is that these images are, because they're so large, they are more like an 2D explorative space, meaning that the image contains an infinite number of smaller sub-images that the user is able to discover, so he can explore the image. And now having our own viewer gives us the opportunity, while the user is exploring the image, to adapt some parameters to the content that the viewer is currently looking at. So for example, one thing that we can adapt to is the tone mapping of the images. For example, if the user is zooming into a dark region of the image, we can brighten things up. Or if he's zooming into a bright region in the background, a hazy region, we can stretch out the histogram to fill the full dynamic range and essentially remove the haze and provide a better vision. So we will talk about that also in a minute. Another thing that we can adapt is the projection of these images. So most images that you see are in a perspective projection, meaning that they are essentially projected on a flat plane. So for example, if you take apart your camera, you have something like a small hole and a lens, and all those rays from the outside world are going through that hole and are essentially mapped to a flat sensor plane in the back of your camera. So this is what you see in this diagram here. So we have here, we have the small pinhole there, and on the right we have a bundle of rays from the outside world coming in, and they get projected straight through the pinhole to the sensor plane on the back of the camera. And now, essentially what our gigapixel camera is capturing is this bundle of rays that you see on the right side here. And if we want to display now an image on our screen, what we can do is we can kind of put a virtual projective surface behind this virtual pinhole and then paint it by intersecting the incoming rays with it. So in some ways you can think of, if you want to display a picture on your screen, of taking your screen and putting it into the world of those rays and then painting it by intersecting with those rays. Now one problem with perspective projection is that as the angles get wider, we get some distortions. And you can really nicely see in this diagram the kind of distortions that we have here. So for example, you see those two pairs of rays, the purple pair and the red pair, and they have maybe about the same angle between them. But then the purple pair of rays hit the projective surface much closer than the red pair. And now if you imagine when this goes to the limit that you have two rays that are almost 180 degrees apart, those would hit the projective plane, maybe miles apart. And so in fact what this does to your image is it essentially shrinks all the scene to the center of the scene, because the most extreme rays kind of determine the interval of your projective plane that you have to map to your computer screen. And this means that as angles get wider, the relative part of the center rays that you see in the center here gets smaller in relation to the whole image. So you can see this shrinking on the image on the left here. And at the limit at 180 degrees, you reach a singularity where all your image is converged to a single point. Okay, in order to avoid this, we can turn to a different projection where we essentially wrap our projective surface around the pinhole. And so it is part of a cylinder, and this is why it's called a cylindrical projection. And here, this has a nice property that the purple pair of rays and the red pair of rays are spaced equally apart on the projective surface. It's essentially a mapping of a linear mapping of directions to locations on the sensor plane. And if you do this both horizontally and vertically, you have a spherical projection. Essentially, your projective surface is part of a sphere. So that allows you to display the full 360 by 180 degrees field of view. But it has distortions on its own, as you can see in this image on the left. So basically, straight lines get mapped to curves. So there are reasons why you want to have both types of projections. So perspective is great because it's most similar to the way humans perceive the world. So for example, all these straight lines in this room, you perceive them also as straight lines. And the same goes for perspective projection. It has the property that straight lines in the world get always mapped to straight lines in the projection. But as we saw, we have distortions when we turn to wider angles. In that case, we can turn to cylindrical or spherical projections, which allow us to display the full field of view. But this comes at the cost that straight lines get mapped to curves and has kind of a flat feeling when panning around, as you will see in a minute in the viewer. So both the types of projections have their advantages. What we really want to have is we want to have the best of both projections, and this is what our viewer provides. So to turn to some images, here on the left side you see what this panorama of Seattle downtown looks in a perspective projection. And you really can see that in the periphery of this image, you have excessive distortions. Things get stretched a lot. And in contrast, the cylindrical projection in the center of the screen looks quite fine. And at this zoom level, our projection is exactly the same as the cylindrical projection. Now, if we start to zoom into these images, the perspective projection starts to look better. And the cylindrical projection is still fine. But as I said, you can see really a lot of lines here that are mapped as curves that should be straight in the real world. And our projection at this point is somewhere in between those two projections. Now, if you zoom in even more, the perspective projection is just perfect. And at this point, our projection is essentially the same as perspective. And the cylindrical is also fine. But again, you see a lot of lines that are displayed curved instead of straight. So putting it all together, our projection is essentially, as you zoom in, it smoothly blends between a spherical, cylindrical, and perspective projection. Now let's have a look at this in our Injective Viewer. I really hope that this is working right now. Ooh. So maybe. Okay, let me try something. So we had it here, right? Will? Yeah. This is really unfortunate. Okay. Wonderful. Okay, so here you have this Seattle downtown image again. And now this is in a perspective projection. Now when I zoom or when I pan around this image, it really gives you the feeling of turning your head around, which is nice. So it's just great. But as you start to zoom out, you see that things kind of start to get distorted. You see that the sides of this image are stretched a bit. And in the limit, if you really zoom out, I mean, if you do this for a 360 panorama, you get a better effect because you have more image data there. But it kind of converges to a single point at some point, which is not nice. And in contrast, if you use a spherical projection like this one, you can really nicely zoom out of this image. But first of all, you have these curved lines here. And also, it gives you this flat feeling when you turn your head. So it feels like you're shifting a cardboard in front of your head rather than turning your head. And now our projection, in contrast, so when we're zoomed in, it's exactly the same as a perspective projection. So you have this nice feeling. But as you zoom out, it smoothly transits to cylindrical projection. And it's really hard to kind of see this transition going on. OK, so at this point, I'm turning over to Michael, who will show you another kind of viewer.
How do I get back to slideshow? OK, so as I mentioned in the beginning, these images are also very deep. And so we would like to do also be able to change the tone mapping on the fly as well. For example, this area is very bright. And so when we zoom into there, we have low contrast. And it's a very bright area. We'd like to be able to darken it and enhance the contrast. And likewise, in this other area, things are very dark. And we should lighten them up. And in fact, as you'll see in a moment, what our viewer will do something like this. When we're looking at a region like this, we get a result that looks like this. When we zoom into this hazy region, it increases the contrast on the fly. Now, I'm going to and there are basically two curves which control this. One is called the key curve. Essentially, this one is saying that let's look at the piece of the world we're about to view. And what we would like is for the key, essentially the average color, to change. So, for example, if it's a totally black image, I want to leave it black. If it's a totally white image, I'll leave it white. And if it has a sort of an average color, I'll leave it as an average. But if my key is generally dark, I have an ability to brighten it up down here. And if it's generally very bright, I can bring it down. And that's essentially going to give us a little bit of extra room also to stretch things out and increase the contrast. We also do something to the range, which is that if our range is low, we get to increase the contrast based on essentially the range. The range in our case being we look at the histogram on the fly of the piece of the image we're looking at. We take the first percentile and the 99th percentile, and that's the range that we're going to expand or shrink, essentially expand. So I now want to show a different demo. In this case, is this, and this is what we were looking at a moment ago from Johannes was our research viewer that has a lot of debugging things built into it, and we can do a lot of experimentation. HDView is something we've developed over the past year since this research was done, and something that's now public. So any of you sitting there with your laptops, if you've got wireless connection, you should be able to go to this page right now and find HDView. It's a viewer now. It's going to run inside the browser, in this case inside IE, although it'll run inside Firefox very soon as well. And this is our page. Here you'll find a lot of things just about the viewer, some pointers to the paper. There's some other people who are now using HDView. There's an instruction on how you can create your own HDView content, essentially by stitching your own images. And we have a piece of code in here which will generate a web page for you from your content. And if you click on this large image, we saw this one a moment ago. This is a mountain which is a bit north of here up in British Columbia, and it's a favorite mountain of climbers. And so if we carefully go in and look, we can actually find this climber here up on the wall, and in fact we follow the rope up, we'll find his buddy up there. Now all this data, as Matt mentioned, is stored in a multi-resolution pyramid, and what that does is lets us just fetch data on the fly very rapidly. All this data is now living out on the net. We've looked at this picture quite a bit, and let me take this one. And again, now let's look down at this region here, for example. As I zoom in here, you'll notice that things start to brighten up. It's as if I had an auto exposure in my video camera. And again, if I come back out, things are kind of bleached out a little bit, and it slowly evolves back to a new exposure. Kind of a more surprising thing on doing this auto exposure is if we zoom in over here on this very hazy region. And probably if I didn't tell you anything, you wouldn't notice anything going on here other than my zooming into this region. But in fact, if I wasn't doing that contrast enhancement, this is what I'd see. So let me zoom back out now, and let me do that again. So I zoom in here, nothing is changing. Okay, and now let me turn it back on. And now we're going to zoom into here. What you'll notice is that contrast is enhanced on the fly. As I zoom in, essentially it does a haze removal because the haze has compressed that contrast. And there's a lot of other images to explore here. We were looking at this one a little while ago. This is a really fun image. Just all this data is on the net. And a fun thing to do in here is to start looking for airplanes coming into SeaTac. In fact, there's a whole string of pearls of airplanes in here. And again, I think you can see the contrast enhancements that's happening on the fly, especially as we zoom into the mountain. We can even go in and see who's up here looking at Seattle from the Space Needle. And finally, although I think our imagery is kind of nice, there are some other people who have started to put things. X-Res is a professional company that shot a lot of wonderful images of Yosemite and other areas, and this is now just pulling data off of their website. So we scan across. I won't flip through all these. There's some really wonderful images. I really like this one of Boston. You can begin to make up a variety of stories of what's happening down on the street, all the way out from this point of view. And likewise, Bradford Bahonis is a local guy who's been doing a lot of panoramic imagery as well. Has some really wild and crazy. I'd really encourage you to. There's a house in Seattle. He's actually taken the Mars imagery and put it up here as well. But these are all rooms within this guy's house. Let's see, where is his? Well, this is his actual bathroom, as far as I know. And again, you can sort of see this is his office. Yeah, hard to tell the difference. Yeah, this is his office, right? Sorry. Anyway, there's a lot of nice things to explore on here. I would, oops. No, I should have brought that back up. Do we have that one still? Where were we? I don't know. All right, I think I'm going to quit then. So here it comes. And finally, if I go back to the home page, the other thing you'll find on here is a map. Matt has started to assemble. People have, once we've put this up on the web, people have started to send us their own content. And so we're actually starting to get a lot of email of, you know, I made this panorama, check it out. And the ones that we like go into sort of a favorites page of this map. So go out and, you know, capture your own content and send us a pointer to it, and we'll put it on the page. With that, we'll quit. Thanks a lot.
So let's take one or two questions before the next speaker.
Sure.
Let's see. Let's start with one of our external guests.
Yeah, so I'm just wondering, what do you do with the external content that wasn't radiometrically calibrated? I mean, if you don't have the camera information.
I mean, other people out there are creating these in their own sort of pipelines. Most people, what they do today, because they don't use the stitching part of it, is most people, what they do today is they fix the exposure on their camera. Like, so I talked to the X-Res guys, they just go out and fix the exposure. But the downside of that is they lose a lot of the nice high dynamic range aspects of those. These scenes are just, you know, when you capture that much data, they're necessarily high dynamic range. So at some point, yeah, we'd like to release the authoring part of this too, but right now we just have the viewing part.
Actually, I had one, I'm going to make one more comment. I had one more slide that I just added at the end. This is really talk in a discussion with Matt. One way to think of HDView, or a viewer like this, is it's really a camera, right? What we captured out there, we didn't actually capture an image. We captured a slice of the light field, right? We captured a set of rays, and somebody could have captured a different slice of a light field. It might have had more rays. And in fact, HDView is really exactly what you do with a camera, right? You stand up somewhere, you get to point the camera, you get to zoom in and zoom out with the camera, you get to adjust the exposure, and you know, if you had a really fancy camera, you could even adjust the film plane. You know, maybe I would tilt the film plane or curve the film plane if you want. So you can sort of think of this as a camera, and that what I would encourage you guys to do is go out and capture little pieces of light field, you know, as deep and rich as you can. Put them up there, and then here's a camera for you to go take pictures of that piece of light field.
Okay, let's see. I'll take one more question from Aaron, and I'll invite Danny to come up and start setting up this talk.
What about the addition from the cylindrical to perspective projection? How do you decide
whether? Yeah. So there's two parts of that detail. I should let Johannes go. Also, the place where you'd want to transition is actually dependent somewhat on your screen sitting in front of you. If you were standing in front of a screen, you know, as wide as this wall, and you were standing here, you'd probably want to stay in perspective the whole time, because it would look just great, right? It would look distorted to people standing back there, but to you it would look great. If you're sitting in front of a very narrow monitor, you'd want to set it at a different point. So we just basically picked a point which was kind of your you know, 20-inch monitor at sitting 18 inches out in front of you. There's some other details on how you do this transition to make it seamless, which is in the paper. So, do you have anything to add? Any other questions? Yeah.
Okay, we'll take one more from Grant.
So this transition, I guess I was imagining how to do that, and one way I could imagine doing it is a plane is a cylinder with infinite curvature, right? So you could just transition the curvature continuously. Is that what you do, or?
Yes.
Okay.
you have to do two things. You have to transition the curvature, and you have to and then change the scale. Basically, you think of it as a surface in front of you. It's a flat piece, and you change the curvature and change the scale, or you walk up to it. Yeah,
so exactly. I'm sorry I didn't get to all the questions I know Jim and others had, but please come talk to Michael and everyone else during the lunch break. And with that, it's my pleasure to introduce Donnie Lashinsky.
Thanks, Rick. I don't know, can anybody hear this thing, or?
There might be a slider on there that you have to turn to on. Pull it up. Let's see. It is on.
Okay.
So the person at the back should get that.
Okay. So, thanks, Rick. So, I'm Daniel Shinsky, and my day job is at the Hebrew University of Jerusalem. And today I would like to talk about some work that was done over the past few years with some students and colleagues, both at the Hebrew University and here at Microsoft, where this is my fourth summer that I'm spending here. So this is joint work with Zeev Farbman, who's a current student of mine, and he's right here, an intern this summer as well, and Anat Levin, who's a postdoc at MIT right now, myself, Yair Weiss, who's a colleague at the Hebrew University. He's on sabbatical at MIT right now, and Rick and Matt, whom you all know. So what I would like to talk today about is about the interactive manipulation of images using this image-guided optimization framework. So what do I mean by that? Well, the motivation for this research was that there's a wide variety of kinds of manipulations that you might want to do to images that requires you first to specify some regions in an image. And there's many examples for this, but I will focus on the three applications that we have written papers about. And they are colorizing black and white images, tonal adjustment in images, and matting. And I will say a few more words about each of those applications over the next few slides. So the first application is colorization, and that's where you're given a black and white source, either a still image or a video sequence, and you'd like to augment that black and white source with some chromatic information so as to make it more colorful to look at. You might want to do that with your old family photos, or to see the color of the dress that your grandmother was wearing at some joyous occasion, or you want to do that maybe to colorize like an black and white TV series so that you can run it yet another time in syndication and get some more people to look at it again. This is an interactive process, colorization, because there are many different objects in the scene, and there's no way of automatically telling which object should be assigned which colors. So there should be some kind of a user in the loop who would specify that Lucy's hair is actually red, and some wooden surfaces are actually brown, because we don't have the intelligence of figuring that out automatically right today. And when I speak of tonal adjustment, I'm talking about the process that a photographer usually goes through in a digital darkroom, where you take this raw image that you shot with your camera, and you want to manipulate some parameters that essentially allow you to develop this digital negative into an image that you would want then to print or to show on your screen. And those parameters might involve exposure, brightness, various contrast and adjustments, and color adjustments. And once again, you could manipulate those parameters globally over the entire image, but you can get more effective results by manipulating them differently in different regions of the image. So you have to select images. And you have a before and after pair here. And I think you can see the difference that such manipulation can make to an image. The third application is natural image matting, which it's not really a manipulation in itself. It's usually a step that you do before, say, when you want to take a foreground object in some image and you want to transplant that object onto a different background. what you would need to do is you would need to identify essentially for each pixel in the original image containing that object, how much of that pixel comes from the foreground object itself and how much of it comes from the background, because we're assuming typically in this application this linear blending model, which is known as the matting equation that's shown on the bottom of this slide. And again, it's an ill-posed problem really if you know nothing about the background. I mean, if the background is just a natural image, there's no way for you to figure out automatically what is background and what is not. So, as I've said before, each of those tasks involves typically some region selection that's done by the user. So I would like to illustrate that in a little bit more detail using this colorization example. So these are some images that I stole from a tutorial on the web, which guide the readers step by step through the process of colorizing an image manually in a software like Photoshop. So you start with the black and white image and say, fine, now I have all those different regions. I know that the skin should have skin color, so let me assign that region some skin color. So how do you do that? Well, you have to go and select all the regions, have to basically outline the boundaries of the regions which are skin. And as you can see, this is a complex boundary. I mean, this particular region has holes in it, in this case corresponding to eyes and brows and the mouth. And you can do that using tools like magnetic lasso in Photoshop, for example. But it will take you some expertise and some time to get it just right. Having done that, you can go to a color palette, select a color, and just copy the chrominance components of that color to become the chrominance components of the region that you have just selected. And voila. Oh, okay, I guess we're not quite done because we've only done with the skin and we have a whole bunch of other regions. So we have to keep doing this process a few more times until we get the entire image colorized. Okay, so as you can imagine, this could be a tedious part of your creative task, right? Selecting all those regions. Another example is tone mapping. So tone mapping using software like Photoshop, there are many ways of doing that. They have now automatic tone mapping operators built into Photoshop starting from CS2, I believe. But the good old way of doing that is develop a few exposures from your high dynamic range image, like the two exposures that you see here. And now suppose you want to blend the region of the window from this exposure here with the region of this desk in this exposure there. So in Photoshop, the way you do it is you place each of those exposures in a separate layer, and then you can go and you can paint by hand a layer mask. And the layer mask is just like a weight map that specifies at each pixel how much of it should come from this image versus how much should come from that image. So I guess dark shades here correspond to this image and the brighter ones to that image. And you can get reasonable results this way. You can get an image which is nicely tone mapped, but it could take some time even for an experienced user to achieve such a task. So the drawbacks of this having to select regions, just to summarize, are that you need to be an expert with the tools that are available to you. And even if you're an expert, it can still take you some time to get it right. And also, certain regions are just fuzzy, and they're just very difficult to either paint a mask that would describe them or outline them with a tool like the magnetic lasso. I mean, creating a mask like that in Photoshop, it's not pretty. And what's, I think, is the most important thing is that having to deal with all those selection tasks, it really detracts the user's attention from the creative process or the manipulation that he or she is trying to perform. Instead, they focus on this technical aspect of selecting things. And this is something that we would like to avoid. So our goal was let the user focus on the task as much as possible, and worry as little as possible about the selection process itself. And the interface we've explored for that is brushstroke driven interface, where in order to indicate that you would want to do something to a region, you make a brush stroke inside that region and then associate certain manipulation parameters with that stroke. So for example, here, this is a colorization example. We select colors from a palette and we make some brush strokes, but the brush strokes are inside regions. You see we made some brush strokes on the sleeve, maybe some in the hair, I guess. Difficult for me to see from here. Okay, and we don't really ever have to outline regions precisely. And then magically, the system should understand what is it that you mean by placing a brush stroke here or there and propagate those constraints to the entire image to get like a fully finished outcome. Now, you might not get it right with the first stroke or two. You will have to add strokes as necessary until you're satisfied. So this is an interactive process, and it should be fast. So here's a brief video that shows this a system like that at work for the tonal adjustment task. This was shown at SIGGRAPH 2006. Here we make different brush strokes in different regions, and then we can adjust a bunch of parameters such as exposure, contrast, and color, saturation, etc. And as what you should be noticing is that as parameters are adjusted, it pretty much affects that region, but not much else, or so it appears. So for example, suppose we want to brighten that area under that arch. We make a stroke there, and then we drag the exposure slider. It makes the area brighter without a noticeable change in the rest of the image. We also want to boost the contrast there a little bit, because just brightening things makes them look washed out. And there we go. And we can also go back to previously made constraints or selections and adjust their parameters, until we're happy with the result. So how does that work? What's happening behind the interface? So what's common to all those applications, the colorization, the tone mapping, and the matting, is that really we can think of them as an attempt to reconstruct an adjustment map. That is some kind of a map that specifies a certain value for each pixel in the image, but and the value could be the value of the chrominance channels, so that would be a two-valued vector, or a single number that indicates how much exposure you want to add or reduce in that pixel, or just the alpha channel value of that pixel. And in all those cases, what we want to do is we want to construct this complete adjustment map for the entire image only from a sparse set of constraints, which mean that the value of the function that you're reconstructing only at a select set of pixels, which are the pixels over which the user happened to scribble. Okay. So we have then the following problem. We have some constraints given to us as input, and we would like, so each constraint has a position and an associated value. In this case, I'm encoding the exposure correction using grayscales. And what we would like to do, and green means 0 or unknown, depending on the context. So now, from this sparse data, we would like to reconstruct a full continuous map for the entire image, like so. And what you should note about this map is that typically we want this map to be smooth, except that when you cross boundaries between very different regions, you don't want the map to be smooth. So we are actually we're interested in propagating those constraints in a manner that would allow the propagation process to possess discontinuities, provided that the image that you're working on has discontinuities of, let's say, somehow similar magnitude at the same positions. Okay. So now we get to the math. Mathematically, we achieve this propagation by solving an optimization problem. Because really, all we know is some values that are scattered across the image. And so we need to somehow constrain the space of all possible adjustment maps that would satisfy those constraints. So we go towards an optimization framework, which in matrix notation, we might say that we're actually minimizing this expression. And so x here is a vector in which each element corresponds to the adjustment value for a given pixel. And then g is a vector where you have the values that were specified by the user for those pixels that he bothered to specify this value for. And then we have a bunch of matrices here. So W is this affinity matrix, which essentially tells us for any given 2 pixels how closely they are related. Because what essentially we're doing, because this is a propagation process, each pixel basically tries to figure out its adjustment value based on the values of its neighbors. So W is this matrix that tells for each pixel to what extent he can learn from the values of its neighbors what its own value should be. And then D is a matrix, it's a diagonal matrix which just sums the corresponding rows of the affinity matrix W. And then C is just another diagonal matrix where we have non-zeros on the diagonal corresponding only to pixels which have been constrained. That is, the pixels on which the user has drawn. Okay? And so, so basically, the first part of this expression, you can think of it as being a smoothness term that expresses our desire that the solution should be smooth, while the second term is often called in the vision literature the data term because it wants also the sum of square differences with respect to the target values to be minimized. So we're attempting to satisfy the constraints in a soft manner, not in a hard manner in this optimization framework. Okay, so really the heart of this framework is this matrix W, the affinity matrix, because that's the matrix where you put all your knowledge or about the problem or all your intuition about what the solution should look like, or you can think about it as all your requirements that you have of the solution regarding its smoothness typically. And if we now go over the different applications, then what we have is that here's the affinity function that we've used for the colorization example. So essentially, we just look at the difference between the Y channel or the luminance channel of the of 2 pixels, and we exponentiate that to get a weight function. And this weight function gives couples more strongly pixels which are adjacent, which have similar grayscale values, and it couples in a more loose way pixels which have a significant grayscale difference between them. And this affinity function is actually quite similar to the one that's used in, say, spectral segmentation methods in vision, like the normalized cuts method, except that they typically have their sigma value constant across the entire image, whereas in our framework we compute this sigma as a variance across the local neighborhood, and so we can then this way give appropriate weight to a difference between 2 values. Okay. So for the tone mapping application, we've used a slightly different affinity function, which basically says that assuming that you have 2 pixels I and j, we want the weight to be high unless there is a large difference. We look at the this time at the log luminance channel of the image that we're working on, and if there is a big difference between the values of those pixels at the of the original image, then we allow ourselves also not to have the adjustment map to be strongly coupled for those two pixels. So it's kind of a similar function to the previous one, just a different expression. But it does work slightly better for our task, whereas that previous function works a little bit better for the colorization task. Okay. Then we have this scary-looking expression that we're using for defining the affinity for the matting application. And at first glance, it might seem like there's no intuition behind this this affinity function. I'm not even going to bother to explain the different symbols used in here, but I will just tell you that there's actually a good reason for having this particular expression, because really we're making this assumption. It's in our CVPR 2006 paper, and we're making an assumption that the alpha channel is finely related with the color channels of the image if you look at a sufficiently small image window. And then from that assumption, you can actually formally derive that this is the relationship that you want to have between two adjacent pixels in order to reach an optimal solution. So I'm not going to do the derivation here, but it's in the paper. So going back to the general definition of the system, you might note this is a quadratic cost function. So the advantage of that, it's got a unique minimum, and we can achieve that minimum by solving a sparse linear system. So we just take the derivative of that and set it to 0. So we have this, we get this linear system, which is a large but sparse system. It's got, as I've said before, an unknown corresponding to every pixel in the image. This is the vector x. And it's got the right-hand side, which essentially consists of the constraints that were specified by the user, and it's 0 elsewhere. And we have this matrix, which has just only a few non-zero diagonal. And this could be solved rather quickly using a multi-resolution solver. And once again, I'm not going to go over the details. It's in our last year's SIGGRAPH paper. Or also Rick has a paper last year's SIGGRAPH which describes a solver that's particularly well suited for solving those kinds of systems. So you could use that as well. We've used that. It works great. But even with this fast solver, you can get a solution within some fraction of a second. But you know, if you want this kind of interactivity where you let users go to the sliders and manipulate them, you want something even faster. So what we've been doing is that we've been noticing that we could just compute the influence function that corresponds to each of the user-specified constraints. For a given set of constraints, each of those strokes has an influence a function that basically decays over the image as you get far from that constraint. So in those maps, white shades correspond high values of influence, and darker pixels correspond to lower influence. So you can see how the influence peaks pretty much inside the regions where the strokes have been drawn. And you can solve for those influence functions. For a given set of constraints, you can solve for each of those influence functions. And then the optimal solution is actually just a linear combination of those influence functions. So we take advantage of that property in the following manner. Suppose we want to manipulate, like you've seen in the video, the exposure in that area. So once the user draws this stroke and then he goes to the sliders in order to try to manipulate its value, what happens is that then at that point we save the current solution of the system, and then we solve the system once more to get just the influence function corresponding to that pink brush stroke. And now when the user goes and tags on the slider and say moves it by some amount delta G, we can obtain a new solution just by a linear combination of the previous solution and delta G times the influence function. And that really lets us update things very quickly in essentially interactive rates, even if we do it just on the CPU. Okay, so now I just want to show you some results. So this is one of the colorization examples where we took an image that was originally a color image, got rid of the color, and then we annotated it with some scribbles, and we got this colorized result. So I like to make this quiz now. I let you forget about what you saw, and then now you're supposed to guess which image is real and which image is the colorized one. Okay, how many people vote for the real image being this one? How many people think that the real image is this one? Okay, the rest, I guess, are... So it's about 50-50, actually. I switched the order from the previous time I gave the talks in case some repeat audiences would not be able to do it so easily. Okay. Another cool thing that you can do with this colorization framework is you can recolor objects in images which already have color. For example, suppose we want to change the color of that orange in the middle. So what we can do is we can have a constraint that says every pixel that we mark with white should just retain its previous value. And then we make some color strokes inside that orange, and the orange turns into something that looks like a fat lemon. Actually, to get this to work, we changed the affinity function a little bit to consider not only differences between grayscale values of pixels, but just differences between RGB values of pixels. And we can also apply that colorization algorithm to video. Again, I can't go into the details of what we need to do to make it work. So this is the input video from I Love Lucy. And then those are the user constraints that were entered over about 13 out of the... so in every 6th frame, roughly, we have some users' brush strokes. And while they're sometimes following the outline of regions, they don't really precisely define the regions. And then this is the colorized result.
So this you're doing it in the 3D cube.
Yeah. But except that the only difference is that when we talk about neighborhoods of pixels, we take into account optical flow to make the neighborhood make more sense. And some tone mapping examples. So here's a raw image that I got from Norman Coren, who's a landscape photographer. And I mean, this image is fine, but we can have some more fun with it. We can say we want to achieve a warmer look for the image and increase the visibility of the details in the foreground. So we can do that by locally adjusting color temperature and exposure. Or we can go for a cooler look and adjust the temperature of the sky. Or we can go for a dramatic look and reduce the exposure on the foreground to the point where it's only like a dark silhouette against the sky. And I mean, all of this was done pretty much using a set of constraints that looks like this. So it's really not all that much user input. I mean, I did spend some time getting those images, but most of the time was spent tweaking the actual parameters. That is, most of the time were spent on the creative aspects of the task, not on the technical ones. And you can also improve your snapshots. For example, you have this backlit photograph, which is a very common problem with home photography. So you can, with a couple of strokes, you can salvage some detail from those dark regions. And it's an interactive process. You refine it, as much as you feel the need to. Okay. So you can also fake, well, unless you happen to have one of those coded aperture cameras that Fredo will talk later today about, you could also fake depth field effects in your images. So for example, we have this image which obviously shows objects at various depths. And I can basically let the system know that I want to distinguish between 3 different regions by drawing 3 sets of strokes, one over this bottle in the foreground, and then another one over the bowl in the middle, and then another one over the faraway objects. And then I can associate like a Gaussian blur with different radii to each of those sets of strokes. And then I can apply this as an adjustment map to the entire image after it's been propagated. And I can get effects like this one where the foreground is out of focus, or like this one where the foreground is in focus and the background is out of focus. And finally, those are some matting results. In all of those images, you have the input image on the left, and then you have the user input, the brush strokes that the user indicates which parts are foreground using a white brush stroke and which parts are background using a black brush stroke. And those were the mattes on the right that were extracted as the result of applying this optimization, solving this optimization problem. So those are the results that I'd like to show today. So just to summarize, so hopefully I've convinced you that this image-guided optimization framework could be a useful tool for quite a wide variety of local image manipulations, and that it's also a simple and a fairly intuitive user interface. And by using a fast solver and this incremental update mechanism, we can get the interactive performance that we need in order to be able to work with this, in practice. That's it. Thank you.
Okay, let's take a few questions before we break for lunch. Alyosha.
So I always wonder how does one measure the ease of use of these kind of systems? So for example, there you have this beautiful Lucy video, right? That you have every 6 frames you do some strokes. But the question is, since this is an interactive system, how did I guess Anat do this? Did she just do every 6 frame once and then it more worked, or did she go back and added some more strokes? Or so how many iterations, how many loops through the system does one need to do?
Yeah, well, those are actually 2 separate questions. So the one question is how to measure this. Really, I mean, you have to do user studies, and this is something that we haven't done. So I mean, we have not tried to time a given task with our system as opposed to with the competing tool. It should be done, I guess, in principle, but we were aiming at SIGGRAPH and not at HCI, so we didn't do it. Okay, as far as the second question, so I mean, when the interactive system you've seen here, this is something that we've worked on while doing the tone mapping work. During the colorization process, we had no UI actually. So actually, Anat went through the painstaking process of annotating images in Photoshop, saving them to disk, and then running a MATLAB script that would produce the result. And yes, it did take multiple iterations to get it right. Although with experience, you can figure out that certain areas will require your input. So I mean, you benefit from experience in this system as well. But I agree. I mean, it would be really nice to have this a more formal study of usability. One more thing that I like to make, one more comment that I like to make is that I mean, this the framework here. I mean, it's not. I think it's not applicable only to this case where you use this brushstroke-based interface. I mean, in principle, you could have some kind of smart algorithm, like an oracle, that would tell you, oh, the exposure here should be this, and the exposure here should be that, and here you should correct the color like that, and then just use this as a means of constraint propagations. But how you get the constraints? I mean, just using this brushstroke interface is just one way, So. Even though all of the examples I've shown used it, but I mean, the framework is more general than that.
Other questions? Brad and then Hughes.
Well, with the video, you showed the example of you didn't use every frame. Have you applied this to like similar photographs? One of the things I think I see with professional photographers have problems with is they've got 100 photographs that are fairly similar, or at least 10 photographs that are similar. And it seems like you might actually be able to just take this from one image and apply it to similar.
Right. Yeah, actually, yes, we have. I mean, there was work that was published in the rendering workshop with it was a student from Tel Aviv University with myself and Danny Cohen-Or, where we took this idea of, given one image that has been colorized, how do you learn the colorization that was applied to that image and you apply it to additional images which have similar setup. And that's really great if you take a bunch of pictures of like in a photo shoot. You take a bunch of pictures and then you want to modify them all in the same way. You can do that. But I mean, it's a different process. I mean, there the key issue is to learn the similarities between a pair of images, and then you can just import the constraints. And once again, at some places you'll be more certain about constraints than in others, and you can let the system fill in the gaps between those areas where you're certain about what you're doing.
Use?
Process what? Yeah, I guess, you know, we haven't considered this particular case. I mean, what would happen in actuality is that indeed this discontinuity would not have much of an effect, because there are constraints which are compatible on both sides of the discontinuity, but we didn't try to do anything smart with that. No, not sure I get it.
So, just for the benefit of people who are, you know, the taping, Hughes asked about a stroke crossing the discontinuity, and then he said something that could extend far away from the stroke. And if I understand correctly, once you've gone over discontinuity, that whole figural contour could be tagged as being irrelevant, right? So there's other information. These optimization-based techniques are, in a sense, very myopic. They're only talking about what's happening at each pixel, and then they use the fact that there are discontinuities of the image to sort of stop propagation. But there are much more semantic segmentation things that I think maybe Alyosha will talk about this afternoon. And to me, it'd be a very interesting topic for discussion, maybe at the end of the day, whether segmentation and these kinds of more constraint-based systems have a way of playing together. Mm-hmm. So, okay, if there aren't any other questions, let me make an announcement about lunch. Basically, you're all on your own. We have a selection of wonderful foods in our cafeteria, just in Building 112. So why don't you all make your way over there and pick out whatever lunch you'd like, and then we'll reconvene here at 1 o'clock.
Can we leave our stack here?